should I speak English? I think I should say, because we know English probably so far, and we are also in one of the best scientists actually from United States. Nader, I don't know, Nader or Nader? Engheta'yı. He's from UPenn, University of Pennsylvania. And I'd like to introduce just a very, very brief intro. He's a Nedwill Ramsey Professor at University of Pennsylvania in Philadelphia with affiliations in departments of electrical and system engineering. The system engineering actually it used to be in Caltech, but it disappeared. It seems still in UPenn. Yeah. Bioengineering, material science and engineering, and physics and astronomy. He has everything actually. One thing is missing is mathematics and chemistry. But since you are dealing with materials, we can count on chemistry. He got his BS degree from University of Tehran, and then Masters and Ph.D. from University of one of the best universities in the world, in Caltech. And his current research activities span a broad range of areas, including photonics, metamaterials, nano-optics, graphene optics, electrodynamics, imagining and sensing inspired by eyes of animal species, microwave optical antennas, and physics and engineering fields of waves. He has several awards from different institutes. One of them is 2018 Pioneer Award in Nanotechnology from IEEE Nanotechnology Council, and 2017 William Schreifer Scientific Achievement Award from IEEE Photonics Society, 2015 Gold Medal from SPIE, 2015 Fellow of United States National Academy of Inventors, 2014, from today to it goes back, 2014 Balthazar van der Poel Gold Medal from International Union of Radio Science, and it goes on like this, it's non-countable things. And he is also has a Wheatstone lecture in King's College London, 2013 inaugural SINI Award in Engineering, 2006 Scientific American Magazine 50 Leaders in Science and Technology, Guggenheim Fellowship, and IEEE Third Millennium Medal. He's a fellow of 7 international scientific and technical organizations. It goes on like this. I'm now tired of counting them. Now, floor is yours, sir. Now we are.
Thank you very much for your kind and generous introduction. Let me start this one. It's a pleasure and honor for me to be here. I would like to thank all of you, particularly the rector of the university, Professor Karaca, and my friend, Professor Eldar Veliyev, and all of you for your kind invitation to me to be here. I'm very humbled and honored to be here. In my talk today, I'd like to talk about one of the areas of the research activities that we have in my group, which we call it the, can you hear me well? Okay. Which we call it the metamaterials. But particularly, I'd like to talk about metamaterials at the limits. I'm going to explain to you what I mean by that, and then we're going to talk about a couple of special cases that we are studying today. Now, in my group, we are interested in waves and fields. We love waves. We would like to manipulate waves in order to do interesting things with that. And in order to manipulate waves, we need materials. So that's how the connection between light and matter come into play. So particularly, we would like to actually do this type of manipulations of the waves and fields at the extremes. And I'm going to explain to you what I mean by the extreme. But let's start from the basic. And we all know that the wave-matter interaction is governed by, let me go back to this, is governed with the laws of electrodynamics. Both classical electrodynamics, Maxwell's equations, so on, that we love, and also quantum electrodynamics, quantum optics, and quantum field theory. But regardless of which approach we choose, we usually like to parameterize this interaction. And those of you who work in waves and fields, you're very familiar with these parameters of permittivity, which electric properties, permeability, magnetic properties, conductivities, which relates to the transport of electrons, and nonlinearity, and so on and so forth. But in nature, nature has provided us with the so-called natural materials that come from periodic tables and the derivative of periodic tables that we like to use. And for these natural materials, those parameters I mentioned to you have certain range of values. But of course, as scientists and engineers, we are never satisfied with what we are given to. We would like to go to the next stage. So the natural question we like to ask is that, could we actually make materials that have those parameters with the values outside the range that the nature has given us? Obviously, of course, physically realizable. And that's where the concept of metamaterials come into play. The concept of metamaterial is actually pretty straightforward. What it is you start with a host medium, and then you embed them with a so-called, we call it inclusions. But these inclusions are man-made. You make them. You make them with the specific shape that you want, with the specific materials that you want. But the interesting point is, as the wave is propagating through this, and by the way, one thing I forgot to mention, I'm talking about electromagnetic waves, but the concept I talk about can be applied almost to any form of waves you want. It could be acoustic wave, it could be mechanical wave, it could be stress waves, and so on and so forth. But my topic would be on electromagnetic and optical waves, but it could be extendable to others. So as the electromagnetic wave propagates through this, is going to excite this induced dipole moments, and those dipole moments re-radiate. So for the observer sitting outside, looking at this structure, to that observer, it looks like you have an effective parameters. This combination of all these interactions can be parameterized, can be homogenized as certain parameters, like what we talked about before, but the values of these parameters will be different. And one of the interesting points is these values depends on these, variations. It depends, of course, on the composition of these materials, whether they would be metal, whether they would be semiconductors, and so on. It would depend on the alignment and arrangement of that. It obviously depends on the density of this. It depends on the host medium. But last but not least, it depends on the shape and geometry of this. And particularly this last point is the one that in the past 20 years have played a very important role. Why? Because with the advent of nanotechnology and nanoscience, you can make these structure in the nanoscale. You can make it with the very accurate dimensions, and that actually gives the ability to create a composite medium, an engineered medium that will have a property beyond what each one of these provides. Now, this is very important to emphasize that these effective parameters are not just the average values of this. They actually go beyond that, and you will see some of the examples as we go through. Now, in the past 20 years, there have been tremendous growth, by the way, in the field of metamaterials. And here I'm showing, by the way, some samples of the metamaterials from different groups all over the world. And this list, by no means is exhaustive. I can show you pages and pages and pages of examples of metamaterial different groups have made. But one of the interesting points is that because now you can actually make these unusual structures, and you can actually have those parameters with the values that you like to have, that will actually allow you to have fascinating applications that previously have not been possible. For example, let me show you some of the terminologies, and some of you are familiar with that. Cloaking, for example. Can we make a material that we can make things invisible, particularly in the microwave regime? Can we actually make lenses that would actually have a resolution better than regular lenses? Can we actually have cavity structures, now becoming a little bit more technical from optical point of view, that the size of it would be extremely small? Can we actually design a material that manipulates the optical beam in any way you like to have, not just the standard what the lens does? Can we actually have very novel electrically small antennas particularly in the microwave regime? How about near zero index photonics, which I'm going to talk about today? In other words, to actually make a material in which the index of refraction would be near zero. What interesting physics and engineering we get out of that? We introduced a new topic that I'm going to talk about briefly, which I call it optical metatronics. In other words, that's a combination of metamaterial and photonics and electronics to have nanostructures that behave as a circuit elements, and to have a metasurfaces, which is basically the two-dimensional version of metamaterials. Now, of course, there have been a lot of activities in these fields. And usually, by the way, in any fields, when we get to a certain level of development, a natural question scientists ask, and that is, what is the next step? What's going to happen in the next 10 years in this field? And of course, I mean, nobody can guess exactly what's going to happen. In fact, sometimes people ask me, can you guess what happens to this technology, 5 years from now? Well, it's impossible to actually predict what happens to science in a field, but even more complicated and difficult to predict the technology. Technology is harder to predict because it depends on many other aspects, just in addition to scientific aspects. But of course, all of us can make some predictions. And one of the predictions that I've been making in the community of metamaterial is being inspired by what one of my scientific heroes, Richard Feynman, mentioned in 1959. Richard Feynman was a Nobel laureate in 1965. In 1959, 6 years before he got the Nobel Prize, gave a talk at the American Physical Society. And the title of his talk was this one: "There's plenty of room at the bottom." And what he meant, by the way, essentially, he gave a blueprint of what was coming in the future, which is now we call it nanotechnology and nanoscience. In other words, what he was saying that if we have the ability to control atom by atom of a structure, then we can actually revolutionize many fields of science. And he turned out to be right, by the way. Several decades later, we do that by actually controlling atom by atom. So inspired by his vision, so we kind of asked like a similar question in metamaterial. And the question we pose is this one: can we have plenty of room at the extreme? And what do I mean by extreme? We're gonna talk about it in a second. By extreme, I mean, can we actually make materials whose parameters would have extreme values, would have a zero value for index of refraction, would have, for example, dimensionality would be 1 atom thick, like a graphene? Can we actually do information processing at the nanoscale? In other words, could we actually make, a computation by only, structure that would be just a fraction of a wavelength, and so on and so forth. Now, these type of, question and inspiration have led us to a series of interesting projects that currently is going on in my group, some of which I've listed over here. And there's no time to go through all of them. For my talk today, I decided to pick 2 of these topics and talk about it. And if any one of you are interested in the others, I'd be more than happy to talk to you, offline. So let's start with the topic number 1. And I call this topic Metamaterial Machine. Now, what I mean by that, so we know what metamaterial is. I gave a brief description. And I heard, by the way, right now that my good friend, Professor Yasser Abu Mustafa, was here recently, talked about machine learning. So he and I were classmates, at Caltech when we were a graduate student. And so I'm in physics, and he's more in mathematics. So one of the things that I've become interested recently is how to actually look at the concept of metamaterial to see whether we can actually connect it to the machine learning. Now, so one of the questions we are posing is, can materials actually help and interact with machine learning in 2 different ways? One is, can we use machine learning to design materials? Okay, that's one direct way. But another way is that, can actually we use material to do machine learning? And I'm going to explain to you what I mean by that. As one specific category of this question, we are posing this question: can we actually have a metamaterial that would do informatics? And what do I mean by that? Can I actually make materials that would do signal processing? And let me be more specific. Can I actually make a material that would solve equations. In other words, can I actually design a material that when I send a wave through it, when it comes out, the wave comes out of that material would be solution to an integral equation that you like to solve. So, Serhat, this goes back to the discussion you and I had this morning. In other words, I would like to resurrect the idea of analog computing. But let's do it in the nanoscale. So let's see what we can do. But before we do that, we pose the following questions. If I want to use light and matter to do computation, so let's get inspiration from the other form of computation we're already familiar with, and that is electronics. Now, we all use electronics for computation. But if you look at electronics, one of the fascinating characteristics of electronics, which often, even in electrical engineering, we overlook, is the fact that the electronics is modularized. In fact, the first course we teach to our student, we teach circuit elements. We teach them resistor, capacitor, inductors. We take that for granted, but the fact that the electronics are modularized have been tremendous help in the design because you're looking at it as a block diagram. Photonics, on the other hand, have not been like this before, but we decided to change that. So we decided to say, can I actually modularize photonics? And we posed this question, by the way, it was like 14 years ago. With the metamaterial, can we actually modularize photonics? And what do I mean by that? Is that, can I actually have a nanostructure with the proper material such that when you illuminate this nanostructure with laser or with light or with microwave, can that nanostructure behave as a circuit element? Can I actually have optical capacitor? Can I have optical inductor? Can I have optical resistor? Because if I can, and we showed that we could, then that becomes your new alphabets. And you can put them next to each other, and you can design infinite number of possibilities. I call it alphabets of a photonics. The same way that we have alphabets in a language, if we learn the letters and put them together, you have sentences, paragraphs. We do that in electronics already, but we wanted to do this in photonics. So what we did, in 2005, I introduced this concept. I said, if we start from electronics, which we are all familiar, this is, Faculty of Electrical Engineering, and we know capacitor, we know inductor, we know resistor, then we showed that it is possible, both theoretically and experimentally, that if you have nanostructure with the proper shape, proper material, proper dimensions, then if we illuminate that with light, each would behave as equivalent of a circuit element, but with light. And in fact, experimentally, we verify that in the mid-IR by a material silicon nitride, and in the near-IR with indium tinoxide, which behaves as lump circuit element. So this actually created a lot of interesting possibilities. And this goes back, by the way, this 2005 was the first paper that we published. And then we did the experiment some years later. And then this actually opened up an interesting possibilities that now if I have this nanoparticle next to each other, I can do filtering, I can do amplification, and so on and so forth. Well, that was in 2005, 2007, and so on. But now what we are doing, we have extended this. What we are doing, we are taking this concept into three different directions. One direction we are taking into quantum aspect. In Serhat, we talk about quantum aspect. In other words, the same way that the quantum optics behave, the way you can basically quantize electromagnetic field, we ask ourselves this: can we actually have a quantum circuit that would work with these nanoparticles? And this is one of the active areas of research in my group right now, that we are doing a quantum optical metatronics. So if you have a system of a quantum system with excited atoms over here, we are showing that the same procedure that electrical engineers use to actually have equivalent circuit, you can do that in modularizing the Hamiltonian of a quantum optical system. And that can simplify formulation of quantum optical system, and as a result, you can actually solve many interesting problems in that regard. So that's one area. Another area that we are taking this is we are combining this concept of metatronics that I mentioned with the one atom thick structures. Graphene, for example, two-dimensional material, for example. So for example, one of the proposals that we had, that we proposed it came out in Science magazine in 2011, we said, if we have one sheet of graphene and we have different doping in different parts of that one single sheet of graphene, then this graphene would look like a collection of circuit elements, a collection of capacitors and inductors. But these are one atom thick circuits. One atom thick circuits in the mid-IR. It's about 30 terahertz frequency. That was a theoretical proposal we had. 1 year after our theory paper came out, 2 experimental groups, by the way, both of them good friends of mine, Dmitry Basov from University of California, San Diego, now he moved to Columbia University, and Frank Coppens from ICFO in Barcelona, in Institute of Nanophotonics, experimentally verify that indeed it's possible to have an interesting electromagnetic surface wave along this, along the structure. In our theory paper, we proposed theoretically that this would be possible to have one atom thick optical waveguides. This would be the thinnest possible optical waveguide you can have. And as I mentioned, you know, my 2 friends, Dmitry Basov and Frank Coppens, experimentally verified the presence of these surface waves in graphene. And this has opened up an interesting possibilities to see how we can do this type of optical manipulation in graphene. That's the second scenario. The third scenario, which I'm going to talk about mostly today, is that can we use metamaterial for informatics? So we know, by the way, that if we start with circuit element, those of you who are in design of the circuits, you know that you can actually put these circuit elements together and you can have an electronic processor. A good example of that is the smartphone that we have. But then with this inspiration, we said, okay, now we know that if we have nanoparticles, which we call it optical metatronic elements, can we put these nanoparticles of materials together in order to do information processing like that? So 4 years ago, we proposed this idea that you can actually design a material, inhomogeneous material, such that as the wave goes through it with an arbitrary profile, by the time the wave comes out, the profile of that wave has changed such that the relation between the profile of the output and profile of the input is the mathematical operation you like to have. So for example, we design a material that would take the derivative as the wave goes through it. We design a material that can take integral as the wave goes through it, can take the convolution as the wave goes through it with that one. And one of the low-hanging fruit applications we were thinking about, and Typhoon, this might be of interest to you in the imaging aspect, is that we propose this idea that what if we actually design a layered structure, which let's say in the order of about 1 wavelength, such that as the wave goes through it, it would take the second derivative of that. Now, why second derivative we decided to work on? Because second derivative is a very well-known operator in image processing. It's an edge detection. In image processing, if you send a wave through it and you actually take the second derivative of the distribution of intensity, you get actually edges of the object. This is very well known, by the way, in image processing community. But the way they do it, now they actually get the pixel and they actually do it electronically to take the derivative. But this proposal that we have, it would do it in analog way. As the wave goes through it and actually gets the edges there. This work that we did in 2014, and this was a theoretical proposal, actually excited the community, and several subsequent works were done by other groups showing that indeed it's possible to have a meta surfaces that can actually take the derivative of this there. But then again, this was like 4 years ago. But what I'd like to do to tell you what we are doing now is this work. Oops. It went very fast. Okay. I don't know how it goes so fast. Okay. Okay. Let me go slowly. Now, what we'd like to do now is to design a material that solves equations. Because we already shown that we can actually design a material that performs mathematical operations. So we put our goal higher level. So let's be ambitious. Let's try to actually design a material that solves a general integral equations. Now, we're all familiar with this integral equation known as Fredholm integral equation of the second kind. Now, the input function is this, is arbitrary input function, you put it there. This kernel, of course, let's say known, let's say a specific operator you're looking for, and the function g is unknown. So can we design a material that when I put this arbitrary function into it as a wave, what comes out of it would be the function g. So that means actually I can solve the integral equation by just sending the wave through it. Essentially what I'm trying to do is to resurrect the concept of analog computer. And you're familiar. This is a different picture that I took this morning. So this analog computer, I mean, many of you in the audience are very young, but I've been around several more years than you have been. And I remember, by the way, analog computers of 1970s. Analog computers were actually very powerful machines. They were actually faster in some cases compared to digital one. But the reason digital computer took over and became so powerful was because digital computer is programmable. Analog computer of those days were not programmable. They were bulky, they were lossy, they were power hungry. But now with the advent of nanotechnology, we pose this question. If I can design a material that would do the same thing, I can bring this concept, hopefully with the nanoscale, much lower power and probably much more powerful and much faster. So this is our goal. And by the end of my talk, in the beginning, middle of my talk, you'll see that we are able to do that. In fact, we just finished the experiment, a couple of months ago, and we are writing the manuscript on that. So the idea is that, okay, if I want to do that, first I have to design this material, but we already know how to design that. That I already mentioned to you. We have to design a material that would do this operation. Okay, that's just operation of integration with this, kernel. But this by itself doesn't give me the solution to this equation because I don't know what G is. I know what I is, but I don't know what G is. In order to get to that, something is missing over here. And in order to do that, I have to introduce a feedback. If I introduce the feedback into the system, and then I bring an arbitrary input into this, then this system basically will give me the solution to this equation. So essentially what we have in vision in mind is to have a system that have a recursive path. And this kernel is the kernel that we have to design. And then you have an arbitrary input, and as a result, what you come out would be the solution to the integral equation. So let's see how we can do it. Right now, we are working on 2 platforms. By the way, this is work in progress, literally work in progress. As we talk about here, my students and postdocs are working on this. So one approach that we are doing is this one. We call it metamaterial with inhomogeneity, which I'm going to talk about right now. But we also have another approach that we are working, and that is a collection of Mach-Zehnder interferometers. There are advantages and disadvantages of each of these approaches, but in the interest of time, I just talk about only one of these over here. So let's go back to this integral equation. By the way, one thing I forgot to mention, in order to keep the problem as general as possible, I'm assuming that this kernel is a very general kernel, meaning that this kernel is translationally variant. In other words, this kernel is y comma y prime. It's not y minus y prime. Because if it was y minus y prime, then this could be a convolution. And that can be easily done with the Fourier optics. I don't want to do that. I want to do it in the situation that I cannot use convolution. And that means this has to be y comma y prime. That's one thing. And the limit of integration arbitrary. It's not from minus infinity to plus infinity. So clearly, this is not a convolution integral. Now, so what we need to do is we need to design a material that would do this. That when you have an arbitrary function coming like this, the output would be this operation. Okay, that's one aspect of that. But that's not by itself is not enough. I have to create a feedback around here. And again, that by itself is not enough. What I need to do is I need to bring the arbitrary input using the directional coupler. And after this settle, I have to get the output over here. Essentially, what I'm looking at is something like this. Now, those of you who work in optics, you may look at this and say, well, wait a second, this is like, N-ring resonators. Yeah, it does look like N-ring resonators, but it's very different. Because this guy over here is a very special material that couples this N-ring resonator. And that's the key. The key is to have this material designed over here. And that's our metamaterial. That's actually the brain of the system over here that we have to design. So in order to do that, first we said, let's just look at the forward problem. Before we decide, in other words, you give me the integral equation, I have to go and design that material. But at first, to see whether we are on the right track, we decided to start the forward problem. In other words, we decided, okay, first start with the scatterer. Try to find the kernel of this, build an integral equation on this, try to solve it, and then compare it with the exact solution to see whether we're on the right track. And if we are, which we were, then we go to the actual problem. So we decided to first study this. So a bunch of scatterers, nothing particular over here. You excite it at different ports, and you look at the output, and you build the kernel, which comes, oops, I don't know why this doesn't come. Okay. For some reason, this didn't show up. There should be a matrix over here. Now, but then we have to put a feedback. So we designed a feedback system around here. And now let me assume I come and put that arbitrary input into the system. And this is a numerical simulation. This is a simulation of that. So you notice that I put the 1, 0, 0, the input here. So this is input, nothing here, nothing here. This system goes over here. Remember, because of this guy, everything is going to be coupled together. And now what we need to do is to come over here and read 3 complex numbers. And according to our theory, that 3 complex number set should be the solution to our integral equation. So let's read that. But in order to see whether it is indeed the solution, we have to compare it with some other approach independently. So we can use an exact result using Mathematical, for example, and you compare it. And this is a result of comparison. The solid curve is a real and imaginary part of the result of this simulation of the structure, and the dashed one is the exact solution we expect. Of course, the agreement is very good. So that was encouraging. Then we changed the input to 0, 1, 0. Again, the agreement is very good. And then, of course, another input, the agreement was very good. So this was encouraging. But that was not the problem we wanted to solve. We wanted to solve is you give me the integral equation, and I go and design the material. So it's okay, let's do that. So let me assume I start with an arbitrary kernel. There's nothing magic about this kernel. This kernel is just basically a separable kernel with not y minus y prime. So now we have to design this material. So there are several optimization techniques one can use. We decided to use the technique known as objective first inverse design. And this technique has been used by my good friend Jelena Vukovic from Stanford for completely different application. So we use that optimization technique for our application. And the system goes through this optimizer. So you start with a clean slate, and you go through this optimization to create this kernel, and you get this distribution of materials. So what you see over here is an inhomogeneous distribution of permittivity, values between 1 and 2. There's nothing magic about 2. We just arbitrarily choose 2. But you notice there's a gradient variation over here. Now, this is good news, but the problem is this is not practical, because if I need to have a material with epsilon 1.3, maybe I don't have that material. So we decided to binarize this, and when you binarize it, you get this one. Now, this is interesting. This binary structure over here consists of only one material, and air. In other words, the dark region that you see over here is material with epsilon 2, and the gray region is air. So essentially what you do is that you get a piece of material, and you make holes in them. But you make holes in them specifically through that pattern. That's what I call this thing a Swiss cheese, because it does look like a Swiss cheese. And that can be easily made, and we have made them. And you're going to see that. Not this particular example, but a different one. So then we see what happens if I send the electromagnetic wave through this. This happens. So this is a numerical simulation of this structure. You notice very, very non-periodic. There's nothing periodic about this structure. You see it looks very unusual. But when you come at the output of this and you measure the output of this, it will give you the kernel you want. But this is not the solution to an integral equation yet, because there's no feedback yet. So what we need to do is to create a feedback. And now let's create a feedback, and let's have this input into this. Now this input, by the way, even though it looks like 0, 0, 1, 0, 0, this input is not a digital input. The only reason I say 1, it means just 1, it means a continuous wave with the magnitude 1. That's what it means. But this basically means 0, 0, nothing, and 1 CW, and nothing, nothing. But if it goes over here, you notice it goes over here, and now what you do, you come over here, and basically you're going to look at 5 complex numbers over here, and this 5 complex number should be the solution to that integral equation that we have. And then compare it with an exact solution. You see, the agreement is very good. Now you might say, wait a second, there's a little bit of change over here? Well, that change is because we have this directional coupler about 10% feed over here. You can make this thing closer to this by reducing the directional coupler here. But that's just a minor engineering improvement. So then we change, different input. So this is an arbitrary input over here. You have something like this. Obviously, the output would be different. But that output is a solution to that integral equation for that input. Now, one thing I have to emphasize, by the way, you might say, well, but you had to design this structure. Yes, you have to design the structure. But when you design it once, that's it. You don't need to redesign it for any different input you want to say. So the input could be anything you want, as long as this structure is designed for that kernel. But the input in that integral equation should be anything you want. So you design this once for that kernel. So we were encouraged. We said, well, let's try to do experiment now. In order to do experiment, we decided to do experiment in microwave first. Now, we always do that in my group. I always like to start the experiment in microwave because it's bigger. I can see the size of it. I can try to understand, the field distribution. And after that's successful, then we're going to take it to the nanoscale. So in order to design this, we said, okay, now that we want to design it, let's just try to have some crazy kernel over here to see, how powerful this technique is. So we decided to use this crazy kernel. Now, this kernel, by the way, doesn't represent anything physical phenomena. So we arbitrarily chose this kernel mathematically. But intentionally, we chose this kernel to be as general as possible. For example, it's complex. It's non-separable. You cannot have one region only y, another region y prime. And it's not translationally invariant. You cannot write it in terms of y minus y prime. So in principle, general. So when we go through this optimization to find what material would give us this kernel, this what we got from our optimization. So this is a Swiss cheese that's designed for this kernel. Now, because we wanted to do a microwave experiment, we decided to use a material that's readily available, so we can easily buy that. And we decided to use a material known as Ruxolite, which has a dielectric constant of 2.53, an imaginary part almost 0. So this is the structure that we decided to build. But before we built it, we did many simulations over here to see what happens to the wave propagation inside of this. By the way, one thing is interesting. You notice that when I showed you, I had a feedback system. But when we decided to actually do this, another idea came to our mind. Rather than to have a feedback system from outside, we decided a feedback system from inside. So rather than to have 5 ports here, 5 ports out, we decided to use the same 5 ports as input and output, just to save on the real estate, so to speak. So that's why we put basically some lossy material over here to bring the light back. And then you send, 5 arbitrary signal over here, depending on your input. And then you're going to look at what comes out. And that's coming out would be solution to your integral equation. So simulation result, this is still simulation. So we choose an arbitrary input. So let's say like this, we have 5 parts input like 0, 1, I, 90 degrees out of phase, 0, 180 degrees out of phase. This input, arbitrary input, goes through this. Look at this structure. We call it Swiss cheese. And what is coming out, we are looking at the 5 complex numbers that are coming out. And now let's compare that. So horizontal axis is the number, is the name of the waveguide. Waveguide 1, waveguide 2, waveguide 3, waveguide 4. You notice there are 4 curves over here. Let's walk through that. There are 2 dark ones, these guys. One of them is the real part. The other one is imaginary part of the simulated result of that structure. And the thin one are the exact result we expect. And again, the agreement, very encouraging for us. So I said, okay, this is the time to start building this now. So this is the rendering of the picture that we decided to build. In fact, a member of my group, Brian Edwards, did a great job over here. He included every detail that you see over here in the simulation, even including the size of the cable that we have to bring to put it over here. Everything was taken into account in this before we start building this, and we build it. So these are the photographs of the structure that we built. And so this is the top view. This, you notice there are these 5 waveguides. There are 5 cables coming out as our input, 5 cables going out as the output of this. We did the experiment, and let me show you the results. And we are very excited about this. So the first set of results we got is that we had the input 1, 0, 0, 0. So there are 5 curves over here. Actually, there are actually 6 of them. The orange one is the input. So input at waveguide 1 and nothing at waveguide 2, 3, 4, 5. And there's a green one, which is the imaginary part is 0 for that. But now let's look at the outputs. So there are 3 outputs we have over here. One is the theory, and that means what do we expect as an exact solution from this integral equation. The other one is the simulation result of the structure, and the other one is experiment. And of course, the agreement turns out to be excellent. So we're very, very excited about this. And then, of course, we did the other inputs in the experiment. So this actually turns out to be that the experiment almost completely matches the simulation that we expected through this. So we are very excited about this. Right now, we're writing the manuscript on this. But our vision is to extend this into the silicon photonics. We would like to take this into the near IR and do it with the silicon photonic technology. Now, one thing I forgot to mention, by the way, if you look at this structure, I forgot to mention the size of it. This is about 4 wavelengths by 8 wavelengths over here. Now, we are working in the microwave for this, which is about 4.3 gigahertz. So the wavelength is about 7 centimeters. So this is about 1 foot by 2 feet. Now, of course, this is just a test of the proof of concept. But now imagine we take this into silicon photonics. If we take it to silicon photonics, that becomes just few microns. So essentially what it means is that by having something in the order of few microns by few microns, we would be able to solve an integral equation. So that would be the analog computer of the future. And we have plans how to do it. So here is the vision that we have. This. So we would like in the future to see the massively parallel system of this. In other words, each region of this would be few microns by few microns. Each of these may solve different integral equations. And if we can combine all of this together, could we have a system that in the future, hopefully in the near future, we can actually solve the parallel, massively parallel integral equation in an analog way using near IR signal. And one of the interesting points, by the way, the technology, in fact, the materials of that could be already available. GST, germanium intermediate telluride. These are the materials that you can actually reconfigure. And in fact, the technology that you're all familiar with, rewritable CD, is based on that material. And you can rewrite your CD. That you already know. In fact, it's already past technology. But that technology can be resurrected for this purpose. In other words, in the future, you can actually basically, with that technology, basically print your analog computer. That's our goal. That's what we want to do. But let me just leave you with one other interesting point before I go. You notice I put here FPGA. Many of you may be familiar with that. This is field programmable gate arrays. This is something that made electronics a very powerful platform. Field programmable gate arrays. And that's what many, many electronic material is based on that. Digital electronics is based on that. You can actually use the same hardware, but you can program it to do different things. That was missing from analog computer. But now I'm very excited to see whether we can bring that concept into metamaterial. In other words, could we have a programmable metamaterial? A metamaterial that can program and changes, and it evolves. And that's why I would like to connect it to the machine learning. In other words, could we use this material that from the result of that, materials actually would learn and actually change its shape, change its kernel, and then evolve and solve different integral equations as we go through it. So this is something that we are very excited to do it in the future. For the remaining moments of my time, by the way, how much time, how am I doing with time? Am I okay? Okay. So that was one extreme scenario I wanted to talk about, but now let's switch gears. Let's talk about a completely different scenario. And this scenario is something that we call it the near zero index photonics. Now, we are all familiar with index of refraction in photonics. Obviously, index of refraction, we use something. But then, I'm going to tell you the history of how I got interested in this. But before that, I tell you the history. Let me tell you a preview of coming attraction. In other words, what would happen if the index gets close to 0? Okay, so let's do this. Okay. Now, we all know, by the way, if I pick any material, any standard material, glass, water, and so on, with the index of refraction greater than 1, we know, of course, the wavelength becomes shorter, obviously. So naturally, the question is, what would happen if I have a material in which the index of refraction becomes close to 0? And in that case, the wavelength stretches at the frequency of operation. And is that good? And actually, if the wavelength stretches, that means any object you put inside the material would look small compared to the wavelength. Even though the object could be large with respect to outside wavelength, but in that material, the object looks small. And if that's the case, what interesting thing we can do? So let's see. So we call this near zero photonics. But now, one of the interesting points, one of the fundamental points is this one. Of course, in optics and in electromagnetics, we love to use Maxwell's equation. So if I look at time harmonic Maxwell's equation, the first thing, by the way, they teach us in electromagnetic course in undergraduate is that if I have Maxwell's equation and I consider the DC scenario, in other words, omega equal to 0, then of course, electricity and magnetism will be decoupled. But you can ask the following question. Is it possible to have a material in which, even though your field is dynamic, in other words, changing with frequency omega, you can still decouple electricity and magnetism from each other? Now that at first looked impossible, but actually metamaterial can do that. In other words, if I design a material in which permittivity and permeability would be near 0 at the frequency of your operation, then this right-hand term becomes 0, even though omega is not. So then you can actually have the electricity and magnetism will be decoupled, even though the field is changing with time with the frequency omega. Now this could give rise to quite a fascinating possibilities, because from spatial distribution, look at this, curl of H is 0, curl of E is 0. That means from the spatial distribution, looks like the static distribution. But of course, it's changing with time with frequency omega. So from temporal variation, they're dynamic. And that is one of the consequences of index of refraction to be near 0. Now, before I go to the next rest of my talk, let me clarify something. Because usually when I give a talk, at this point, people would, in their mind, say, wait a second, something doesn't look right. Because if the index of refraction is near 0, the phase velocity becomes larger than velocity of light. Is that possible? Would it, violate a special theory of relativity and so on? No, it would not. You can have phase velocity larger than velocity of light for the CW system. In fact, we do that all the time in a waveguide near cutoff. If you work with the microwave waveguide and you operate it near cutoff, effectively phase velocity is close to infinite. What matters from special theory of relativity point of view is the energy velocity should be less than velocity of light. Information velocity should be less than velocity of light. Group velocity should be less than velocity of light, not the phase velocity. In other words, these materials have to be dispersive. They have to be function of frequency. You cannot have them independent of frequency. That would violate causality. But you have to have it function of frequency. And in fact, we did the experiment, and indeed, that's the case. So as a result, obviously, group velocity is less than velocity of light. Everything is fine. Causality is satisfied. Special theory, everything is OK. So there's nothing wrong with that. So you can rest assured that the physics is untouched. And we did the experiment. So one of the interesting possibilities we were thinking about was the following. Imagine that you have a waveguide, a simple waveguide. You have two metallic walls, very, very simple. You have filled with air, and you have a TEM mode propagating down this waveguide, and this is the very simplest possible mode. We're all familiar with that. Now, what I would like you to do is the following. Come over here and break this waveguide, split it in two. Put one of them this side, another one that side. And now you would like to connect this region with a very arbitrary shape, but this shape still is covered with metal, but inside, you want to put a material there. But you want to put a material such that the observer who sits here and the observer who sits there would not know that this section exists. In other words, the observer would be exactly like sitting over here. So in other words, this entire region would be invisible to both observers. Now you might say, well, I can do that with the regular cavity. No. There's an additional condition over here. This shape is completely arbitrary. Regular cavity would not give you that. This shape is completely arbitrary. How can I do that? There's only one answer to that question. The material inside should be a material that permittivity and permeability of that would be 0 at the frequency of operation. In this case, the wavelength inside of this would be infinite. The phase difference between the wave here and here would be 0, and there's an impedance match. So no reflection and transmission would be 1, and the phase of the transmission would be 0, would be exactly like happens over here. So this gives you an interesting incentive that if we can do this, and in fact, I'm going to show you the experiment that we did this, that would happen. So if that is possible, then it's some of interesting physics come into play. For example, this is a numerical simulation that we did before we do the experiment. You have the wave coming over here, this magnetic field distribution. You notice magnetic field over here is uniform, and it changes with time in unison. That's an indication that the wavelength is infinite over here, and the phase is exactly the phase here. In other words, this region in space, even though physically has some size, from electromagnetic point of view, is a point. It doesn't have a dimension. As a result, you can do a lot of interesting, fun things. For example, you can put the two waveguides any point you want. The observer doesn't realize that these are two different points. You can put it like this, you can put it like this, you can put it like this. Reflection coefficient is 0 for this. And the phase is 0. Transmission coefficient is 1. It's better than the waveguide. Okay, now you will see that a little bit later. Now, you might say, okay, before you go any further, do we have such a material in which epsilon would be near 0, index would be near 0? Yes, we do. Actually, we have quite a number of them. In transparent conducting oxide, there's a series of material. Transparent conducting oxide, indium tin oxide, gallium doped zinc oxide, aluminum doped zinc oxide. They have a 0 crossing of permittivity at about 1.19 micron wavelength. The problem is that the imaginary part is not that small. So for some applications, these materials are not good. In some other applications, that's good. But the materials better than this is silicon carbide in the mid-IR. Silicon carbide in mid-IR has a 0 crossing at 10.3 micron wavelength. And that's a CO2 laser. So at CO2 laser, silicon carbide becomes an ENZ material. We call it epsilon near 0 ENZ. In a UV regime, we have topological insulators. Some of the topological insulator material, they have a 0 crossing over here. Now you might say, okay, that's fine. I buy that. There are some materials that have this property, but those are at those wavelengths. How about if I like to have my material at my own wavelength to do that? Then concept of metamaterial can help us to build that. You can actually engineer material to make it ENZ, epsilon near 0, by stacking them, epsilon positive, epsilon negative combination. Or you can actually just pick up a regular microwave waveguide, empty waveguide, and you operate at the TE10 mode, and you operate it near its cutoff. You get some of the properties of ENZ. If you want to do it in the visible domain, you can do with the photonic crystals. C.T. Chen from Hong Kong University of Science and Technology showed very nicely that with the proper design of this, you can have a material, you can have a photonic crystal that has a Dirac dispersion with accidental degeneracy, and effective index becomes 0. And my friend Eric Mazur from Harvard shown that you can actually do it with the integrated system as well. Now, let me take you into history. Almost 13 years ago, in my group, we actually posed a very simple question. The question we posed was this one. We have this system, so we decided to start with a very simple, let me actually show you here. Let me start with this, okay. That was the paper, but now I'm gonna show you. So at that time, we asked this question. Imagine I have a parallel plate waveguide. Very simple one. PEC, PEC, TEM mode coming like this. And I have another waveguide, very simple one. Now, we pose this question. What happens if I connect these two waveguides in a very arbitrary way? Completely arbitrary. This shape is completely arbitrary. The only condition is this is perfect electric conductor, which we call it PEC over here. And this is a two-dimensional structure, just for mathematical sake. And air over here, and there's one mode of waveguide, which is TEM mode is coming. Okay, what happens to that mode? intuitively, what do you think should happen if you have this unusual arbitrary intersection? You would expect that some of this wave reflects back, naturally. But then we pose this question, what if I come over here and, it doesn't work? Oh, it's messed up here, okay. That you fill this region with the material with permittivity near 0. By the way, this was just purely a what-if question. We didn't have any applications in mind. It was just a curiosity-driven question. What if epsilon equal to 0? What happens to this? Now, you might say, why was I interested in this question? Well, one interesting point, we know if the permittivity is 0, index is 0. If index is 0, phase has to be uniform. No phase variation. So that means the phase here should be the same as phase there. So that means I have to have a radiation over here. About conservation of energy, I have to have less radiation there, reflection there. So that was our thought. But there was another intuition was against that if I'm inside the material, that material has a wave impedance, which is the square root of mu over epsilon. So if epsilon is near 0, that impedance is very high. And the impedance over here is 120 pi. So there's going to be huge impedance mismatch over here. So if I have huge impedance mismatch, do I have any field over here, even though its phase could be uniform? So these two intuitions in my head were contradictory. So we decided to solve this problem. Mario Silveirinha, who was visiting my group, and right now he's a professor at the University of Lisbon in Portugal, we decided to look at this problem analytically, theoretically, and we got lucky because we were able to actually solve this problem analytically exactly to find the exact expression for the reflection coefficient, which is this one. Now, on the face of it, this, okay, may not interest you. We say, okay, this is some reflection coefficient. But we decided to see what happens to this reflection if you want to make it 0. So in order to make this 0, I have to make the numerator 0. So I have to make the real part and imaginary part 0. So in order to make a real part 0, I have to make A1 equal to A2. Okay, that's fine. I can make the two waveguides the same height. That wasn't interesting. But then imaginary part has to become 0. But the imaginary part is multiplication of 3 parameters. If I make any one of them 0, I achieve my goal. First, K naught. But what is K naught? It's omega over C. So if I want to make K naught 0, it means I have to make the frequency 0. Well, frequency 0, it means it's DC. It means if I put a battery over here, I would set the same voltage there. Not interesting, obvious. Or I have to make mu equal to 0. But permittivity of this is already 0. So if I make permeability 0, then I have an impedance match. Yeah, that makes sense. But 12 years ago, we didn't want to touch permeability. Now we are doing it. But in those days, we didn't want to touch permeability. But then there's another parameter over here that I haven't told you about yet. Or we have to make A sub D equal to 0. But what is A sub D? A sub D is this cross-sectional area. Now, this was very counterintuitive to us. And let me explain why. That means if I actually make this region narrower and narrower, in other words, I choke the throat of this waveguide, the wave actually goes through it better. Now, let me repeat that again. It was very counterintuitive. If I keep A1 and A2 untouched, and I make this waveguide, and I make this thing narrower and narrower. I mean, of course, with the exception of touching it short circuit. You don't want to do that. But you make it narrower and narrower, reflection coefficient becomes less and less. That means transmission coefficient gets close to 1. At first, we didn't believe that. We said, oh, it can't be. This is counterintuitive. If I make, we double check, we triple check, exactly satisfy Maxwell's equations and so on. Everything was fine. We did the simulation. Everything was fine. Everything was okay. Later on, we found out an interesting physical, intuition for that, but I don't want to bore you with the detail. But instead, let me show you actually the simulation, and you get an interesting feel to what's happening over here. Oh, one thing I forgot to mention, I'm sorry. Another important factor about this formulation is this formulation doesn't say anything about this angle. In other words, you can actually make this waveguide and bend it 180 degrees. Still, reflection doesn't change. Now, in a regular optical fiber, that doesn't happen. In any waveguide you would do, that doesn't happen. But in this one does. And in fact, you're going to see the experiment. So in this case, we choose this waveguide like this. this is a metallic wall, the wave is going to come, and there's an abrupt, discontinuity over here. Obviously, you're going to see there's a lot of reflection, obviously. And you do. So this is simulation. You see a lot of reflection happening over here. You have a standing wave. Nothing interesting. Now, what I'm going to do, I'm going to fill this region a little bit with the material, and I'm going to try to bring the permittivity of the material from 1 to 0. Let's see what happens. So this one, unfortunately, the numbers don't show up. This is epsilon 1. This is epsilon 0.5. You notice that there's a little bit of leaking over here, but most of it still reflects back. This is 0.1. You notice a little bit goes through, but most of it coming back. And this is 0.001. Everything is going through. It's very interesting. No reflection. Everything is going through this. And you see what interesting things happening over there. So essentially, if you look at two extreme, air, and this would be that material with epsilon 0.001. You notice everything going through this, no reflection, a lot of reflection over here. Three interesting messages we can take home from this observation. Reflection is 0, okay, that we see. And that phase uniform is an indication that the index is near 0. And that means the wavelength has increased there. So we decided to do the experiment. We decided to do the experiment with this, and this is the experiment we did almost 10 years ago. And we did it over here, and this is the magnitude and phase of the transmission coefficient. And you notice that the blue one is the simulation, and the red one is the experimental result. And the experimental result agree both in magnitude and phase. And by the way, it's independent of this L. So you can actually stretch this one still. That doesn't change. So in other words, you can actually do a lot of interesting things. So we decided to do it with a bend. So 90 degrees bent, 180 degrees bent. Again, you see this one. So the example, the analogy I like to say is that if you look at a regular wire in the room, you notice if I get this regular wire and bend it, nothing happens. Now you can do it with the waveguides. So you can actually have a waveguide and you can bend it and nothing will happen to that for this. So how many minutes do I have? 5, but that's fine. I can adjust it, anything you want, yeah. So in the remaining 5 to 10 minutes I have, I want to just give you, so this we're thinking about is that, okay, if I send a wave over here and the electric field is very, very strong over here, how can I take advantage of that? Usually when you have a very high electric field, you think about two things, sensors and nonlinearity. So sensors means what? Means, okay, if I put something over here and I change it a little bit, I can actually detect the variation of that. That's one thing. Second thing is that because I have field coming over here and I have very huge electric field over here, by reciprocity, if I put an antenna there, I can get very good radiation. Now in microwave, okay, that can be done. But I wanted to do this in optics. So I was dying to see how I can actually do this in optics. In other words, can I design this material at the nanoscale and then put an optical emitter there? But what is an optical emitter? Excited atom, excited molecule. If I can put it there, that molecule should emit hugely there. But then how do I put actually molecule inside of this? So as I was thinking about this, in one of the presentations that I have on the theory of this several years ago, my good friend Albert Polman, at that time he was the director of Institute of Nanophotonics in Amsterdam, in Amolf. After the coffee break, he came to me, he says, I do have actually an equipment in my lab that can help you put that optical emitter that you like in your structure. And that equipment he was talking about is cathedral luminescence spectroscopy. So for 1 week, I went to Amsterdam, and we put our heads together. I'm going to show you what we built there. But first, let me tell you about the equipment he has. He has this equipment which is called cathedral luminescence spectroscopy. And electron beam is coming out. There's a parabolic mirror. There's a hole there. Electron beam goes through it. You put your sample there. Electron beam is coming. When it hits the sample at that point, it emits photon. And that's known as a transition radiation. And the photons that's emitted is collected by this mirror, comes through the lensing system, either goes through a spectrometer, so it would tell us the intensity as a function of wavelength, or you can actually put it through the CCD camera, and you can actually map the radiation pattern of that. That was fantastic because this electron beam has a footprint of about 4 nanometer by 4 nanometer. So we can decide exactly where we put it there. So I went there, and together we designed this waveguide. Remember, this waveguide looks like that microwave waveguide I showed you, except this is in the nanoscale. This is about 2 micron. About 85 nanometer, the height of it. And we built several of them with different width over here, and this is covered with silver. Electron beam comes from the top, hits this one, goes through the silver, goes through that waveguide, and at that point emits. So you can actually put an optical antenna anywhere you want inside that waveguide with a resolution of 4 happens. You notice that the phase is uniform. So no matter where you put that electron beam, this thing happens. Essentially what I'm saying is that you put an antenna there, the E and Z would look like you are extending the near field of antenna. So you can put the antenna anywhere you want. This created a lot of interest. And so Albert and I continued our collaboration. We built other systems. But let me jump into, where is the, can I actually ask you to forward the presentation? Well, actually, I can do it myself. Let me jump over this one. Thank you. So then we decided to look at other interesting features of this phenomenon. Many of you may be familiar with the process of known as superconductivity, known as Meissner effect. Meissner effect is superconductivity. If you have a superconductor, let me actually show you here. If you have a superconductor and you put a magnet on top of that, the magnet would be levitated. This is a known phenomenon in superconductivity known as Meissner effect. What happens is the magnet, because of magnetic field vectors, the superconductivity expels the magnetic lines. As a result, the magnet will be suspended there. Okay. Now, superconductivity, of course, is electromagnetic. It's a quantum physics phenomenon. But to the observer sitting over here, the observer would look at the structure and from classical point of view, looks at the superconductivity and says, okay, the vector B is 0. But when the vector B is 0, it means mu is 0. So in other words, this is equivalent of mu being 0. So if mu being 0, vector B is 0, everything is expelled. So we said, well, we have a material in which epsilon is 0. So kind of like a dual of that. So in superconductivity, mu is 0. So we have a material epsilon is 0. So it means vector D has to be expelled. So if the vector D is expelled, what would happen if I have an electric dipole? Put it over here. Should the electric dipole be levitated? So we started asking this question. And it turns out to be, we got an answer was better than what we originally thought. Yes. This is a theoretical result. Yes. We showed theoretically that if you put a dynamic dipole on top of this, the dipole can be levitated. And levitated as a function of permittivity of the substrate. It turns out that it doesn't have to be only 0. Any permittivity between -1 and +1 would do. And one of the interesting points is that if we add loss to the substrate, still the effect would be there. This theoretical paper came out 4 years ago and created a lot of interest. And now, together with 2 of my friends, Pino Strangi from Case Western Reserve University and Onofrio Morago from Messina in Italy, and my group, together we are trying to prove or do the proof of concept of this experimentally. It's a very tough experiment. And the idea that we would like to do, and we are in the middle of it, is that to see what happens if we have a particle, nanoparticle, and we illuminate it with a laser, create that dipole, at the frequency for which the substrate is E and Z, would this particle levitate? If that happens, theoretically we show that it should happen, but remains to be seen in experiment. If that happens, that means that you can actually have particles above the surface that would not have any friction. So that would be fantastic, by the way, in microfluidic system. In that case, you can actually send the fluidic system on top of the surface without the friction of the particles, which could have interesting applications. And again, I don't have time, but let me jump to the end. One of the interesting byproducts of this is that you can actually have a cavity system, that this cavity system has a resonant frequency that's independent of its shape. Now, those of you who are very familiar with optics, you know that if you have a cavity And the resonant frequency of a cavity depends on the shape. If you get a cavity and you change its shape, its resonant frequency will change. But in this scenario, we proved that it's interesting to have a cavity system in which you have an electromagnetic mode that's independent of the external shape of the cavity. And this is a numerical simulation. I'm going to give you also the experiment in a second, and then I stop. Is that if you have a cavity with the arbitrary shape, with the permittivity near zero, let's say like a silicon carbide, and you put a dielectric core over here, these are the electric and magnetic field distribution of the electromagnetic mode of this. But I would like you to bring your attention to the following interesting scenario. If you sit in this shell, you notice that you have an electric field, but you don't have any magnetic field. This is what I mentioned a few minutes ago, that you can have a scenario that electricity and magnetism are decoupled. This is interesting. In other words, you sit over here, you measure an electric field that's changing with time with frequency omega, but it doesn't have any magnetic field. And this is possible in this type of material. Moreover, in this structure, you notice that the electric field comes over here and stops. And let me emphasize one point, that this cavity doesn't have any metallic wall. In other words, this is an open cavity. Now, what does that mean? That means I can have a structure in that open cavity that can sustain and hold electromagnetic energy without being radiated. This is something that we call it photonic bound state in the continuum. In electronics, you see that, by the way, in quantum electronics. But here is the equivalent of a photonic version of that you can actually hold photonic energy in space without being radiated. So you can have a series of cavities. We call it morphing cavity. You can morph this cavity to this shape, to this shape, to this shape gradually, and all of them will have the same resonant frequency. So one of the reasons we are interested in that, because this becomes an interesting building block for a technology, we like to call it flexible photonics. Now, we do have flexible electronics that you can actually have electronic that when moves, nothing will change. Here, that would be interesting for a case that you can actually move the structure and the resonant frequency of that does not change. So let me stop over here. This is the experiment we did in microwave. 3 different cavity, 3 different arbitrary shape, 1 dielectric rod at 3 different locations we put there, 9 different experiments with these cavities. This is the structure built, and all of them have the same resonant frequency. So we experimentally proved this, and this will be possible. So let me just come to the end and give my thanks to my group. This is something on thermal radiation. If you're interested, I can talk to you about that, and let me just stop. In the quantum system. So I'd like to thank those members of my group who contributed significantly to what I presented today. I'm very proud of them. And the funding agencies, I appreciate, the funding and support that they give us. And I'd like to thank all of you for your attention and particularly for the invitation I received from you. Thank you very much.
Thank you very much. Indeed.
Sure.
Probably we have a couple of questions. I know he's tired.
No, I'm okay. Yeah. I'm fine.
He's okay.
Yes.
I just want to know, what's the real difference between the processor found in the quantum computers and the processor that you're trying to do using metamaterials?
Oh, very different. Thank you for the question, by the way. It's a very different process. This is deterministic, by the way. In quantum computer, you have probabilistic aspect of the superposition states between 2 states. Here, no. It has nothing to do with the quantum computer. This, basically, as I mentioned, is an analog computer, but it's doing with waves, entirely with waves. And as a result, you can do it with, as I mentioned, one example that we have shown over here is to do basically processing of solving equations, for example. So it's very different than quantum computer. I hope in the future they would connect to that, but for now, there's no connection.
Thank you.
That was a fascinating talk.
Thank you.
And I enjoyed every second of it.
Thank you, Tucker.
Every nanosecond of it.
Thank you, thank you. You're very kind.
Thank you very much. Your science page contours of the faces such that you will immediately detect if there is a phase or not.
Yeah, we hope
And
so.
and how could we proceed
Absolutely.
in
Let's
a
talk
work
about
like
it
this?
offline. Absolutely. That idea
Thank
that
you.
I propose the idea I proposed in the science paper 2014 was, by the way, that one that I mentioned, it was a theoretical proposal that we have there. But in the science paper, actually, we give the value of the permittivity that would be able to do that. We didn't do experiment on that. That was a theoretical proposal. But yes, that proposal that we had in the science paper, it will give you the second derivative with respect to one axis to that. That second derivative could be applied to any object you want to do that. So that's what I was very interested with what you showed me in your lab with regard to face recognition. We didn't look at the face recognition. That example that I showed you was building, for example. That was just a simple, example that we put there. But yes, it could be applicable. And the subsequent work that I showed you by other groups that came, years later after our paper, they showed that you can actually do it basically for Laplacian operator. And it was in not only second derivative with x, but second derivative with y. Yes. But I would love to talk to you about this, to see how we can do it. Sure.
One last question. Ladies first.
What kind of mathematical problems arise in these investigations?
You mean which one? With regard to the first part of my talk?
Yet, poor mathematical, such as diffraction problems.
Oh, great. Okay, very good point. If you're referring to the geometry I showed, which I call it Swiss cheese, for those scattering that happens in that Swiss cheese structure, that actually is intentional because that actually is part of the design. We have that. Now, but let me add to that. One of the interesting points about that case is that in that particular case, we use, of course, passive medium. Obviously, this is just regular dielectric we have. So we have to choose the kernels that the output of the kernel should be obviously less power than the input, naturally. And that would be passive medium. That's why actually in our design, we had to put some lossy materials in the wall in order to make sure that that happens. That actually was a positive thing because introducing the lossy material would make the Q of your system to go low, which means the system becomes fast. That was a good byproduct of that. But let's say hypothetically you would like to actually have a kernel in which the output becomes greater than the input. But yes, there's nothing wrong with that. You can actually have a system that you have to pump the system. That makes it more complicated, but as a proof of concept, we don't want to go through the more complicated system. We want to start with something that would be more passive. That's one thing. Another thing, by the way, is that we actually did some noise analysis. Because often people ask me this, okay, well, analog computer of the past, they had some problem in the noise. In other words, you have. Here, we actually, the way we did it is we look at the scattering matrix of the system, and we added some percentage of noise to every element of the scattering matrix to see what happens in our simulation to the result. We find out that the result is pretty robust. You can do that. Now, whether you use this and do a cascade of this, what happens to the noise, we don't know that yet. Whether the noise would actually propagate through this or not, that remains to be seen. That we don't know the answer to that. But at least for this one system, we know that the noise is handleable. There's no problem. The general mathematical problem.
Angle between rays and phase waves.
I see. No, we don't. At least so far, we haven't seen any major mathematical issues. The only condition we have is to the eigenvalues of the problem should be less than 1. And that's fine. The whole range of kernels that would fall into that. Why? Because when this thing is coming back and coming back and coming back, it has to converge. And that requires the eigenvalue to be less than 1. One other related to this question I'd like to add, which I forgot, is that people often ask me, okay, you have designed this Swiss cheese structure, you have this. If you change your input suddenly from this input to another input, how long does it take for the system to give you the answer? That's actually a great question, and we just actually finished an analysis of the simulation of this. It turns out that it would be around 300 to 400 cycles of that CW, which is actually quite fast. Now think about it. If I use microwave, every cycle of microwave is about nanoseconds. If I use 1 gigahertz, of course we use 4 gigahertz, so it's about 250 picoseconds. If you multiply that by about 300, 400, you get something in the order of 75 or 100 nanosecond. That's great. But of course, we don't want to stay with microwave. We want to go to the near IR. If we go to the near IR, that becomes in the order of picoseconds. So we are very excited about this. If I change the input and within several hundred picoseconds, I get an answer, I would be very happy with that. That's a very fast computation.
It's pretty simple. Back to the basics. One of the first slides that you showed,
Sure.
that was the interaction between the waves and the material.
Yes.
Very basic.
Okay.
And then the second slide was transformation optics.
Well, one of the application areas is transformation optics.
Is it possible, to, instead of optics, that can be applied to audio waves?
Of course. And people have done that.
Okay.
Oh, yeah. Yeah, that's, I mean, not,
Yeah.
I mean, not as much. I mean, in electromagnetic optics, there are much more activities, of course. Acoustic, metamaterials, there's a whole area of acoustic metamaterial. But yes, the answer to your question is yes, it could be any wave function. People have done that for thermodynamics. People have done that for, believe it or not, even for seismic waves, for earthquake.
Okay.
Yeah, that's right.
Okay.
Interesting. There's, if I can send you the references for the people who have done it. For
That
some
would
of
be
this
great.
acoustic. We don't do acoustic, but there are other groups that they have done acoustic and mechanical waves.
Okay, thank you.
I'd like to thank you again.
Thank you. Thank you very much. Thank you. Thank you. Thank you. Thank you, all of you. Oh, thank you. Thank you so much. Thank you. We can take a picture. Sure. We should stand in front. Exactly, that's right. Oh, sure, sure. Thank you.
Young people, you have to know physics, of course, math.
Not yet. Thank you. Thank you all very much. Thank you. Thank you.